Hello. In this video I'm going to talk about Newton's method of finding roots, or at least approximating roots of equations. This is an iterative method, and is usually included as one of the applications of the derivative in courses on differential calculus. It's a very interesting subject to look at because it leads off in many different directions, and we'll see that as we go through the development. As a first example, I'm going to work with the cubic polynomial x cubed minus 7x plus 2, and we want to know what values of x are they that to make this cubic equal to 0. I've drawn a graph of that here, and there are 3 roots. It's a third-degree polynomial, so it's not surprising we can find 3 roots. And these 3 roots in this case are near 2.5, 0.3, and minus 2.8. That's approximately where the roots are. And Newton's method provides us with an algorithm for taking an initial guess and then approximating from that initial guess towards a value for the roots. Before we get into that, you should be aware that you can change lots of other problems into root problems, and so there's a much wider application of this algorithm. For example, if you wanted to know a value of x such that x equals 8 sine x, you can solve x minus 8 sine x equals 0. You can turn it into finding a root. If you're trying to calculate the square root of 117, you can do it by finding the root of x squared minus 117. So you can actually turn quite a few other problems which don't begin as let's find the places where a function is 0 into a problem formulated as let's find the places where a function is 0. Okay, Newton's method is quite simple. We start with a function here which is in black, and we're trying to find this particular place where the function is equal to 0. The idea is that we're going to make an intelligent guess about where that root is. We're going to make a first guess, call it x sub 0, and then we do the following. We evaluate the function at x0. Well, that means we go up to this point on the graph of the function. So this point has coordinates x0 and f of x0. From this point, we calculate a tangent line, and we follow the tangent back down to the x-axis, and that becomes our new point, x1. So from x0, we go to the graph, follow the tangent, and that's our new point, x1. And then we do it again. We evaluate the function at x1, we go up to the graph, we follow the tangent back down to the x-axis, and that's our x2. And then we have an x3, an x4, an x5. We keep iterating, and as we iterate, we certainly hope that, and it looks in this case as if, we're going to get closer and closer to the root of that particular function. And in many cases, that's exactly what happens. Okay, what I want to do now is go through the details of how you actually calculate that iteration in Newton's method. So this is the same diagram that we had before, and let's look at the first triangle we have here with the green hypotenuse on it here. The rise in that triangle is the value of f of x0. That's the rise. The run is x0 minus x1. That's how far you've run along the x-axis. And so the slope of the tangent line is the rise over the run, and it's just f of x0, the rise over the run, x0 minus x1. And now, though we've done calculus, we have another way of calculating slopes of tangent lines. We use the derivative. And so we can evaluate the derivative of f at x0 and also get the value of the slope of the tangent line. So we have two different ways of getting the slope of that line, and so they must be equal. Now we do some algebra, and we put f over f prime, so that's dividing through by f prime, and multiply through by x0 minus x1, so we rewrite it as f of x0 over f prime of x0, function over derivative, is equal to the change in the x values, x0 minus x1. And now we can rewrite this as x1 equals x0 minus the quotient f of x0 over f prime of x0. That is the basic Newton's method iteration. And this is what we do all the time in Newton's method. You take the function, you evaluate it at your first point, take the value of the derivative, so you have to have calculated the derivative to do that, and we get f prime of x0. And so we take the quotient f over f prime and subtract that from x0, and that's the new value x1. And that's all there is to Newton's method. You just do that, and you do it over and over, and it approximates the root. So the general form is that the n plus 1th x is obtained from the nth x by subtracting f of x sub n over f prime of x sub n. And that's our general iteration for Newton's method. That's really all there is to it. Let's do an example.